Now we are going to introduce a very important topic, that is the Laplace transform. This is a very important topic because, at least for linear systems, the Laplace transform operates what I would define as a change of coordinates, even though it's more sophisticated than a change of coordinates, allowing us to transform a linear differential equation into an algebraic equation. The difficult part about differential equations is that there are derivatives involved, and with the Laplace transform we can remove all these derivatives and obtain an equivalent equation that has no derivatives but has only multiplications and sums. So that's why the Laplace transform is quite important. So what is the Laplace transform? The Laplace transform is an operation that changes a function f of t that we say it's defined in the time domain into another function we call it f of s that is defined, as we say, in the frequency domain. Now this might seem a little abstract still, but it gives a lot of intuition once you become familiar with it. So let's start giving the technical details of this transformation. Just see this as just a transformation, changing a certain function, small f of t, into capital F of s. So the Laplace transform is defined in this way. How do we, if we are given a certain f of t, how do we find this f of s? Sometimes this capital F of s is written equivalently in this way. L, that stands for Laplace, calligraphic L, applied to f of t, giving an argument of the function that s. It's very common to use the lowercase letter for the time domain function and the uppercase letter for the Laplace transform in the frequency domain, but you often find also this notation here, so I want you to be familiar with both notations. However, these are just names. What do you do? Well, the Laplace transform of a function f of t is the integral from 0 till plus infinity of f of t times the exponential of minus st in dt, and this is defined for all values s in the complex domain. So s can be a complex number, no problems, so long such that the integral converges. So some observations about this definition. This is a definition. You give me an f of t, you integrate from 0 to t f of t times exponential of minus s of t in dt for all possible values of s's, such that this integral makes sense. There are some observations that I want to make. So first of all, the Laplace transform is only defined for functions f of t such that f of t is equal to 0 for all t that are negative. So this is the first observation. If f of t has some values for t that are less than 0, then when you're taking the Laplace transform of that function or of another function that has different values for a negative t but the same values for positive t, then the Laplace transform is going to be the same. So in order to make sure that this Laplace transform is a good change of coordinates mapping different functions into different functions in the frequency domain, we have to somehow impose that before time 0 all these functions have to be need to have the same value, and we choose them to be equal to 0. Okay, so this is the first observation that we make. The second observation is the set of all S complex numbers for which f of S exists is called domain of convergence for f of S, or equivalently for f of t. Okay, so different functions have different domains of convergence, and sometimes the domain of convergence plays a role. So as an additional things, the domain of convergence is often omitted because it doesn't play a relevant role in most cases, but in some cases plays a very important role. So I want you to be at least aware. When in a practical use, you'll tend to omit the domain of convergence, but sometimes you bump into some contradictions, apparent contradictions that are resolved once you take into account also the domain of convergence. So that's why I'm writing this in red. Yes, in most situations we can sort of forget that the domain of convergence exists. There is a domain of convergence, but in some cases we have to find out what it is, because otherwise the computations we are going to make don't make any sense. So in some cases it plays a very important role. Okay, so this is the definition. Let's start computing some Laplace transform of some functions that are easy to compute. At least let's start with some simple cases and let's try to see what the Laplace transform of certain functions is. Okay, so let's start. So as a first example, I'd say that we can start with the unitary step. So Laplace transform of the unitary step function. So what is the step function? The step function in the time domain looks like this. It is, of course, 0 for negative t, and then it's equal to 1 for all t that are greater or equal than 0. Where the discontinuity is exactly, if it is 0 at time t equal to 0, if it is 1, actually it is not important. Is not important. Let's go like this. Let's just compute the Laplace transform. You'll see that the Laplace transform is the same no matter where you actually place the discontinuity. Okay, so let's simply compute it. So if f of t is equal to the following function: 0 for t that is negative and 1 for t that is greater or equal than 0, let's compute f of s. F of s is given by the integral from 0 till plus infinity of f of t exponential of minus st in dt. This function happens to be 1 for all non-negative t's, so this is given by the integral from 0 till plus infinity of just the exponential of minus st in dt. Okay, we need to integrate this. So we are going to integrate this quantity here. The integral of exponential of minus st is given by exponential of minus st divided by minus s. Try to differentiate exponential of minus st. You'll see that when you differentiate that with respect to t, you're multiplying by minus s, so this is the integral. But this needs to be computed for t equal to 0 and t equal to plus infinity. This is equal to, and now see how the domain of convergence is going to play a role. So we want this integral, when you are replacing t with plus infinity, we want this exponential to be finite. So when does it happen that this exponential is going to be finite? When t goes to infinity. This happens only if the real part of s is greater than 0. If the real part of s is greater than 0, then this exponential of minus st when t goes to infinity goes to 0. So we have 0 minus, and then we have to replace t with 0. So we get exponential of minus s times 0 divided by minus s. The exponential of 0 is 1, minus and minus cancel each other out, so this is given by 1 by s. So we have found out this. The Laplace transform of the unitary step is 1 by s with domain of convergence. Let's call it D. D is the set of all complex numbers such that the real part of this complex number s is strictly positive. So this is what we have learned by simply applying the definition in this very simple case. So now we start knowing that the Laplace transform of the unitary step function that is often represented also in this way. Sometimes this function here f of t is also denoted in this way. When I use this equal sign with these two dots, it means that I'm making a definition. Sometimes people represent this as 1 of t because this function is 1 for t's that are non-negative, and for negative t's is equal to 0. So sometimes this function, this unitary step, is denoted in this. So we have learned that the Laplace transform of the unitary step is 1 divided by s. So that's the first thing that we have learned. Let's see if we can consider other examples. So let's consider another example. Laplace transform of the unitary pulse of length a. What is the unitary pulse of length a? Well, we define it in this way. Looks a bit like the unitary step, but this is the difference. Of course, it has to be 0 for the times that are negative. I'm going to call this function here p(a) of t, and it is also 0 after a, and between 0 and a it's equal to 1 divided by a. So it has two discontinuities. One is in 0, and the other instead is in a. So this function here, this unitary pulse of length a, is non-zero only from time t equal to 0 till time t equal to a. And what else happens here? It happens that otherwise it is given by 1 divided by a. Why is it called unitary? It's called unitary because its integral is always 1. So if you take the integral of this function from minus infinity to plus infinity, its integral is always 1. So sort of its intensity, even though it's distributed over time, the overall intensity is always given by 1. The only thing that changes is for how long you spread the overall intensity. Okay, let's compute the Laplace transform. The Laplace transform is given by, if this is f of t, if this is PA, then I'm going to call this capital P A of S is equal to the integral from 0 till plus infinity of small p A of t exponential of minus st in dt equal to, now we replace, we have the extremes that matter are only 0 and a, because everywhere else we have 0, and this is given by 1 divided by a here, and here we have exponential of minus st in dt. So not so difficult to integrate this, because 1 by a gets out of the integral. We are integrating again exponential of minus st, so we already know that that integral is given by this quantity. This time the difference is that we are going to compute this between t equal to 0 and t equal to and t equal to a, because the extreme of integration now is a. So now we simply have to compute this. This is given by 1 divided by a times, and now we don't have any problems of anything that is going to diverge, because if I replace t with a, here I get exponential of minus s a divided by minus s minus, and now I have to replace t with this, so I get exponential of minus s times 0. This is an a and this is a 0 minus s. So if I want to write this better, I can write this, let's see, this exponential of minus s times 0 is 1, minus and minus, they go away, so I write this as 1 minus exponential of minus sa divided by let's see, I have minus s, so here I have as. Okay, so this is the Laplace transform of the unitary pulse. What is the domain of convergence? In this case, the domain of convergence is d equal to all the complex numbers. We have no problems here in terms of convergence. Now, if we neglect the domain of convergence and we make a go to infinity, well, then in theory we should get the result that we have here. We'll talk about when we can take these limits later. So far we have this case here. The reason why I have introduced the unitary pulse is that the unitary pulse allows us to deal with some certain entities that are not functions. So what happens when a goes to 0? When a goes to 0, the time when this pulse happens gets shorter and shorter, but 1 by a goes to infinity, so this pulse becomes bigger and bigger in height. The overall intensity, if you integrate the pulse over its time when it's active, it's always 1. So in that sense, the intensity is always the same, but now it's distributed over a short interval, and so to keep the same intensity, the height of the pulse has to go to infinity. In that case, when a goes to 0, we can say informally that we have a pulse of duration that is 0 and with height that is infinity. But that's not a function. We cannot define a function that is infinity for t equal to 0 and 0 everywhere else. That makes no sense. But in the limit, we define an entity like this as Dirac delta. So the Dirac delta can be seen. It's not a function, so I'm not going to write that it's a function. The Dirac delta can be seen as a pulse, a unitary pulse, with duration a that goes to 0. So the Dirac delta, that it's not a function, it's actually called a generalized function or a distribution. It's typically represented in this way. Here we have t, and our Dirac delta of t is 0. This is just a way to represent it. Is 0 everywhere, with the exception of 0, and here we draw an arrow to mean that the value there is something that we might think as infinity. Again, this is not a function. This is not a function. It is, we can define this in a formal way. There is a whole branch of mathematics that's called the theory of distributions, or the theory of generalized functions, where this is done formally, but we are not going to do this in this course. We are just introducing Dirac delta because it has some practical relevance. So this is not a function, it is a generalized function. So since it's not a function, I cannot write delta of t equal to infinity for t equal to 0, 0 otherwise. I cannot write this. And also, if I do, how do I compute the integral of something like that? Despite that, we can compute the Laplace transform of delta of t by taking p a of s and considering a that goes to 0. Let's see what happens. So the Laplace transform of the Dirac delta of s is equal to the limit when a that goes to 0 of p a of s, and p a of s we have just seen is given by 1 minus exponential of minus as divided by as. When we take the limit, now we are going to consider a Taylor expansion of the exponential. The exponential of minus as can be written in this way. So this is equal to the limit for a that goes to 0. We take as as the denominator. Here we have 1. When a is very, very small, the exponential of minus as behaves like this. 1 minus as plus a square s squared divided by 2, and so on. So this is just the Taylor expansion. From here to here, we just use a Taylor expansion. So this is again given by the limit when a goes to 0 of 1 minus 1 plus as minus a square s square divided by 2 and other terms divided by as. It happens that 1 and 1 cancel each other out, so we are left with as. All these other terms are powers of higher order in a, so when a goes to 0 they go to 0. The only thing that is we are left with is as divided by as, so this is equal to 1. So what have we learned? The Laplace transform of the Dirac delta is simply 1. Is a function that is equal to 1 for every s. Okay, and so this is another interesting result that we simply obtain by a limit in this case. Okay, we consider another example. There is no way to have enough examples for this topic. So another example is, this is very simple as well, Laplace transform of the exponential of at. So again, we are considering a function that is not the exponential of at. Remember, everything has to be 0 here, and only for positive t's we are going to take the value of our function. So this is actually what we are considering. So if f of t is equal to 0 for t that is negative and exponential of at for the non-negative t's, let's compute the Laplace transform, and we see that this is going to be very useful too. So f of s is given by the integral from 0 till plus infinity of exponential of at times exponential of minus st in dt, and this is going to be equal to, well, so far we are not going to change the extremes because they're still 0 and infinity, but what we can do instead is to combine these two exponentials together so that this can be written as exponential of minus s minus a t in dt. Now that we have this, actually this is again easy to compute because this is going to be the integral of this is given by the exponential of minus s minus a t divided by minus s minus a, and t has to be computed between 0 and plus infinity. So let's proceed. When t goes to infinity, we have some convergence issues. So when is it true that when t goes to infinity that this exponential of minus s minus a t converges? It happens that we need to have that the real part of s needs to be greater than the real part of a. So I'm writing it here just that we remember. Convergence if the real part of s is strictly larger than the real part of a. Probably you were assuming that a was a real number. There is no reason to assume that. We can assume that a is a complex number, so that's the reason why I'm specifying real part of a here. We are going to use some situations where a is a complex number, so there is no reason to make this extra assumption here. So when we compute this integral here, when t goes to infinity, Since the real part of s is larger than the real part of a in our assumption, this exponential goes to 0. Then we have 0 minus, and when t goes to 0, we have exponential of minus s minus a 0 divided by minus s minus a. The numerator is 1, the denominator is this minus s minus a that cancels the other minus in front of the term, so we are left with s minus a. Okay, observe that in the case when a is equal to 0, this function here, f of t, becomes equivalent to the unitary step. So when a is equal to 0, this should go to the Laplace transform of the unitary step. And indeed, when a goes to 0, this becomes 1 by s. So we find as a special case the unitary, the Laplace transform of the unitary step. So let's write it here. The Laplace transform of the exponential of at, well, multiplied by 1 of t. I want to be precise, at least when I'm introducing this. I can write, I don't like to write this as exponential of at. I want to specify that it is 0 before, for before time equal to 0. So I multiply this by 1 of t, that is the unitary step. So the Laplace transform of exponential of at is 1 divided by s minus a. Doesn't matter if a has a real part that is negative or that is positive, so long as the real part of s is larger than the real part of a, we are absolutely fine in terms of convergence. So this Laplace transform is applied to any exponential of at for every possible a, but it's going to affect the domain of convergence. So these are, I'd say this is enough in terms of the introduction of the definition of Laplace transform. Now the important part that we are going to see is going to be the properties of the Laplace transform.